This presentation is delivered by the Stanford Center for Professional Development.
Great. Well, today we're going to do our, I guess, second to last topic. It's one of the new ones we were very happy to add. It's Stochastic Model Predictive Control, and although in the end it's going to look just like the model predictive control, it's actually worth going over this carefully because there's actually some real subtleties here. This is actually much more sophisticated, in fact, than mere optimization, and I'll make that clear as we go along with it. A lot of times the subtleties are kind of brushed over, and I think in this case it's a serious mistake because it's quite complicated, and you really have to kind of be on your toes to know what things mean and stuff like that. So, okay. Although in the end you'll find out what do you do about it. You use like model predictive control that we looked at last time. So, in some ways you could argue that you don't need to do model predictive control unless it's a stochastic problem. So let's I'm gonna go over this slowly because it's actually a bit it's quite subtle, in fact. So here's what we have. We have a linear dynamical system. So with a state xt and an input ut, and we could make we could easily make this time varying. So that could be at and bt. It's easy enough. And here's the new element is a noise here, a process noise. So what this says is that the next state depends on actually two things. Well, three things really. It depends on the current state. So that's this. It depends on your action. And it depends on this random variable. Actually, at this point, it's not yet a random variable, but it's something. The idea is it will soon be a random variable. And it depends on something that you don't know. That's fully. That's W of t. So we'll use this notation that capital XT is going to be x0 up to xt, and that's the entire state history up to time t. So it's a big vector with all the states. It's the first part of the state trajectory here. Now, when you talk about control or something like that, we're going to make the requirement that the input must be causal state feedback. And what that means is this, that this input ut is a function of the state history. Now, if you're a function of the state history, then you're also a function of the disturbance history. Okay? Because if I know the state, if I know the state sequence, that's what this says. If I know x0, x1 up to xt here, then up here I know that, so I subtract those. I definitely know that because I did it. So I know W of t. So in fact it's just a linear transformation that maps, in fact a linear bijection that would map x0 up to xt to x0 up to wt minus 1. So to say that you are, or to use the language of probability to say that you're measurable on capital XT on the state sequence means that you're measurable on the disturbance sequence actually up to t minus 1, because you know what the last disturbance is, but you don't know what the next one or current one is going to be or something like that. Okay. Now these functions are called, that's called the policy at time t. And then I guess you'd talk about the policy would be a collection of these functions or something like that. We're just going to consider the finite horizon one. You can easily consider the infinite horizon version. And there's a couple of important things to say about this. The distinction in something like stochastic control is that what you're actually looking for are these functions phi t. In particular, you are not looking for a particular u. In fact, it doesn't even make any sense to say that you're looking for u. I mean, in the end, of course, what will happen is we're going to find a u. That's true. But in fact, what you're really looking for is this u that depends on the state history. And let me just say a couple of things about how this, why this is extremely different. It's different this way, and it's very important to sort of understand these distinctions because these are not sort of mathematical subtleties that, you know, don't really matter much. These make all the difference. They make a huge difference in practice, and here they are. It's this. The basic idea here is that UT, you actually have recourse. When you choose U3, you know what X3 is, you know what X2 and X1 and X0 are, and you only decide U3 at that point. Okay, so that's the, so in other words, you wait until information is available. What do you know at, for example, t equals 3 that you didn't know at t equals 0? And you know a lot. You know W0, W1, and W2. So these are things you know at that point. And that's by virtue of, here, of knowing the X sequence, so you know the W sequence, so you know the initial state. So that's actually going to have a real difference. In fact, if you choose U ahead of time, knowing nothing, you will do worse. You must do worse, of course. And the difference actually is going to be sort of the value of recourse. Recourse or feedback or whatever you want to call it. Okay, so let's look at stochastic control. That works like this. The initial state and the sequence of disturbances is a random variable, though we don't assume that they're independent or anything like that yet. We may later occasionally. So this is a random variable. Well, it's a stochastic process, although that's a little bit pedantic to call it a stochastic process since we're doing finite horizon. So, but if you want to call it a stochastic process, go right ahead. And our objective is going to be this. It looks exactly like it did last lecture. So it's going to be a stage cost, that's little lt of xt ut, and then there'll be a final state cost. So this is sort of this is the cost of winding up or whatever, something like that in one of these things. So in a supply chain, that would be some salvage cost or some who knows what, that kind of thing. Okay, in a dynamic system problem, this might, in fact, the whole thing might be, you might be interested in putting it in some final state, in which case this would be less important, and this would judge how far you are from some target state that you wanted to hit, for example. Okay, so we'll assume that these are convex. And what's interesting about this is that J, this objective, now actually depends on these control policies. So these are really our variables, if you want to talk about variables in the problem. So this is an infinite dimensional problem. And in fact, it's in some sense, it's even more than merely like an infinite dimensional control problem, because your variables are actually functions. So even if you do one stage or whatever that has a name, if you just do one stage, your variables, I mean, if there are variables here, there are these actual functions or policies. Okay. By the way, that has nothing whatsoever to do with how we're going to implement it. We may implement it by actually solving specific problems or working out functions and all that kind of stuff. That's a different story. Here, what's important is what depends on what and when decisions are made. Okay, and we'll have constraints. UT is in this script UT, and the stochastic control problem is this: choose these policies phi 0 up to phi t minus 1 to minimize j subject to the constraints. So no matter how you write it down, that is actually a very complex problem, and it's worth actually thinking about what it means. It is not the same as an optimal control problem. An optimal control problem basically says, you know, you're in this state, here's your cost, find me a sequence of inputs. That's just straight optimization. Maybe it's large dimensional. Even in the infinite dimensional case, which we looked at last time, it's not that big a deal. I mean, you just take a finite horizon and that'll approximate it well enough. This is much more than that, because you're actually optimizing over, in fact, not only are you optimizing over sort of these really infinite dimensional function spaces, but in fact this growing set. So, I mean, it's not that big a deal, but it's very important to understand what this is not. What you'll find actually amazingly in a lot of things is it just says the problem is to choose U to minimize J. And that's actually just like wrong, because that's not the problem. It makes no sense to choose U. What you're actually choosing is you're choosing the method by which you choose U when you've arrived at a certain point in time and you've made certain observations. That's actually what you're choosing, which is a policy. Okay. So as I've said, that's an infinite dimensional problem. And the variables are these functions or policies. And there's many things you can do. For example, you can restrict these policies to a finite dimensional subspace. You could say, well, all these policies are affine, for example. You could make it even more specific than that. And a lot of classical control stuff that you'd learn about in like a control class or whatever would be where they don't make a big deal about all this. And these are very specific. You might look at some error and have something proportional to the error, to the running sum of the errors, and maybe to the first difference. And that would be a classical PID control. By the way, if that's the type of control you're doing where you're looking at just extremely simple policies like that, then it's pedantic to even introduce all this and talk about policies and things like that. But that's okay. But we're going to look at the full case here. Now the very important point here is that you actually have recourse. Recourse means you can actually come back and do something about something after you learn more information. So that's what recourse means. It always gives you an advantage. So it basically says, another name for this is like, do I have it here? I don't. Okay, so well, there's lots of names for this. One is called multi-stage optimization, sequential decision making. So actually those things should be up there. So those are other names for this type of thing. And they all kind of make sense. The other one, the very big one, is just feedback. And I guess you're taught about this as an undergraduate. I taught undergraduate classes on this. And you talk about feedback. I guess these ideas come up, but not really fully what it means in an optimization context. And this is what it means. Okay. So the point here is you actually get to change U based on the observed state history. So if you look at a standard optimal control problem, it says basically, here's the problem data. Please decide on what the input history should be to minimize some expected cost. That's a stochastic control. That's a stochastic optimization problem. So even if there's random variables in it, that's no problem. But that's still just an optimization problem. And in fact, in a finite horizon one, it's a finite dimensional problem. Might have some random variables and be a stochastic optimization problem, which some people would have you think is hard. But it's still just an optimization problem. So this would be called, instead of feedback or closed loop control, this would be called open loop. Is what you'd call this. Okay, so now in the general case, the only way to really evaluate this objective here is going to be here. There's going to be some special cases. If these are quadratic and so on, then we're going to get a sort of an analytical solution. And in fact, as usual, that will be essentially that and 15 other special cases will be the only cases where people can solve stochastic control problems. So that'll be the solve, meaning like here's the solution. There'll be isolated ones in one dimension and two and things like that. We won't even look at them, but there are plenty of them. And actually, you can also say the following, that if there's, I don't know, if the state dimension is 1 or 2, you can certainly solve it numerically and get, as close as you like to the solution and so on and so forth. And it's very, very simple. But not in the general case. Okay, so the only way really to evaluate this, except in, these very special cases, is by Monte Carlo. And the way you do that is you fix your policies. So you have some policies. And the policies could be as simple as some affine policy. They could be open loop. You can compare it to an open loop policy. An open loop policy would these functions are very simple. Whenever they're called, they just return they're return constants. They just return some this returns U0 or something. And that's what you're going to do no matter what you observe. And what you'll do is you'll simulate a trajectory of x0 and w, and you will calculate J, and you'll run Monte Carlo, and you can make a distribution of this cost, and then the expected value, in this case the empirical mean, will give you the objective modulo Monte Carlo error. So that's what you'll have to do to judge these. Okay. So here's the solution via dynamic programming. So you can actually say what the solution is here, or you can say something about the solution. And it does, in a few cases, actually just give you, it becomes sort of computable. So let's look at what it is. It works like this. You're going to let Vt of capital Xt be the optimal value of the objective from t on, assuming or conditioned on the fact that you visited the states x0 up through x little t, which is to say that you have this state history capital Xt. So that's your state history up to that point. So conditioned on that, you then let things play out on the other end, which is you would run, for example, to simulate that, you'd start from that point, conditioned. If this is a distribution, you'd work out the conditional distribution for Wt plus 1 all the way up to Wt capital T minus 1, conditioned on this sequence, and then you would do simulations and calculate this optimal value of the objective. Now, we can certainly say what this is at the end. At the end, it turns out that Vt, of course, there's no more action to take, so there's nothing to do. And in fact, there's nothing to do except pay the final bill. So you simply pay the final bill here, like that, and that's deterministic. There's no. This is, in other words, this is x0 up to x capital T, and it only depends on this last component here. And if you take this back to 0, and then the expected value of v0 of x0 is a random variable. This is actually exactly equal to the optimal value of the original problem. I should say something about this before we move on. That you can compare all sorts of other stuff here, and there's two extremes that are actually worth pointing out. Let me just point those out now because it's good to keep these in mind here. So there are two extremes. One is is actually the prescient controller. So prescient control basically says, I will tell you ahead of time what the disturbance sequence is. So prescient means you know the future. So I'll tell you what the demands are going to be, or I'll tell you what disturbances are going to hit your vehicle, or something like that. And if you do that, it's interesting because now because in this case the control policy, it's not causal, of course, it knows the future. And if you actually solve the prescient version, it still depends on the initial state. But that by the way is it's a standard convex optimization problem, finite dimensional. You can solve it. If you run the prescient version, Monte Carlo, starting from different x0s, you will get the average prescient cost. That's clearly a lower bound here. So that's going to be a lower bound. Everybody see what I'm saying here? Now, of course, in some cases, knowledge of the future is going to be a huge advantage. Think finance, for example. So even a small amount of knowledge of the future is going to give you a huge advantage. Actually, in other cases, it might not. So that's one bound. Now, at the other extreme, so that's the full prescient variation, which gives you a lower bound. You can also do the other one, which is the full ignorance policy. The full ignorance policy goes like this. You can do it different ways, but the full ignorance policy is this: choose u0, u1 up to u capital T now, before you know any of the w's. Everybody see what I'm saying? By the way, that's covered by last lecture because that's nothing but that's an optimal control problem, or what people call optimal control. So that's the full ignorance one, and that will of course do worse than if you have recourse, and then the extreme of recourse is to have full prescience. So okay, so this is sort of in between here. Okay. Okay, so let's get back to the solution here. So you have this is the optimal value of the objective, conditioned on this initial state history capital X sub t. Then you get a backward recursion, and it looks like this. It says, well, in fact, you can even say what the optimal thing to do is. In fact, that's the first thing to do. What you do is this. You have observed capital XT. So what you do is this, is you should minimize the current cost of a current action. That's this. That's the bill you're going to run up now here. You know XT, because this is conditioned on capital XT. You know little xt. For that matter, you know all the entire previous state history. And then what's going to happen is, as a result of your action V, you're going to land in this state, AXT plus BV plus WT. That's random because you don't know WT yet, because you don't know where you're going to land. Okay? So what you would wherever you land, you'll have to finish out what you're doing. And if you do this optimally, the cost will be VT plus 1 of where you land here. Okay? So, and this is the state appended at the end of this thing. So that's the cost of where you land. And then this will be conditioned on the expected value of this conditioned on XT. In fact, this expected value goes outside here, but this thing is deterministic if you condition on capital XT, so it goes over here. Okay, so this is the picture. So this is the so-called, I don't know, the Hamilton-Jacobi equation, the Bellman equation, the dynamic programming equation, and it's got a Russian name which I don't know. So anyway, that's what it is. Anyone know the Russian name? Anyway. Pontryagin, we'll just say. Let's say. Okay, so then you get this backward recursion. It's exactly the same as before, except we didn't have this conditional expectation before. So this was not here, and this was just simply simpler, and this was not here either. So what happened in the last lecture was this. When you chose an action, where you ended up was absolutely certain. It was simply AXT plus BV. And you simply had to worry about balancing the current bill versus the bill you run up from landing in a certain state at the next step. Here it's more complicated because even when you commit to an action, you don't know where you're going to land next step. And that's why you have this conditional expectation here. Okay, now you can show that these are convex functions. That's actually quite straightforward because any kind of averaging or conditional expectation is going to preserve convexity. And this is minimizing. If you do partial minimization, you preserve convexity. So these are convex, these functions. Okay. An important special case is when you have independent process noise. So that's when the noises are independent. By the way, that doesn't happen that often. Typically what happens is you transform the original problem so that the noises are independent. And you do that by introducing additional states. So actually, if you've taken these classes, you know about this. But let me just give an example. Let's say in finance, a very common model of something would be a random walk. Okay, so in a random walk, obviously, the variables themselves are not independent. What's independent are the increments, are the differences. And so you'd introduce a new variable, which is the running sum of the w's, and that would be a new state. So that's how this is done. So actually, how many people have seen this somewhere? Oh, good. Okay. In which kind of classes? MS&E or?
W292E, dynamic programming.
Oh, okay. Oh, perfect. Okay, great. How about?
Yeah, me too.
Oh, same? Same?
No, MS&E 251.
Cool. Okay. All right. No one in like Aeroastro 210 or something like that, or did you take it?
We haven't taught that in a while.
We haven't taught 210 in years.
Oh. Well, okay, fine. But had they taught it, this might have been in it.
You see a little bit in 207 A or B, one of those.
B.
B. Yeah, it's the code.
Okay. That's. I thought it was in that one. Okay. Really, years? Oh well. All right. So, okay. So this one actually gives you a solution. In in the typical case. I mean, actually, after a while, you get used to this. You know, if everything's like Gaussian, and actually here you don't need anything Gaussian because it's just second order statistics. But you know, with enough you know, Gaussian, independent arrival, exponential, you know, these kinds of assumptions and linearity and quadratic functions, usually these problems get solvable or something like that. Okay, so we'll assume that here, x0, w0. Actually, you know what? Let me go back to this. So something I didn't finish saying something about this, which I meant to say. Sorry. In this case, when you have an independent process noise, I gave you an example of how you create an independent process noise in the general case. Then VT actually only depends on the current state, and so this is what you would. This is the way these things simplify, and they look much simpler. So V sub t of capital X sub t, you can write as V sub t of little xt because that's all it depends on. And then you get this. And this is actually what you would see in books, more likely. You'd see something like that in books. And then the optimal policy would look like this. By the way, there's an interesting thing here. Because of this expected value, this actually has a smoothing effect on VT. Right? If you have a function v, even if it's sort of non-differentiable, right? If it's got corners and things like that, if it's like an L1 norm, you throw in an expected value, and that actually is going to smooth it out. So these are actually going to be quite smooth functions, or that's actually a smoothing effect. Okay, so let's do linear quadratic stochastic control. So no constraints. These variables are independent with zero mean and covariances, I guess sigma, and then WT, so something like that. That would be sort of the standard, a standard model. And then we take stage and final costs, which are just quadratic, convex quadratic. And you don't really need this RT to be positive definite, but it just it's a traditional assumption. And it makes sure it means it means that there's an equation that's going to come up. Well, the Bellman equation is a formula for it that just always works. But the important point is that these are quadratic. These are convex and quadratic. Well, in this case, the value function itself is quadratic. It, by the way, is not a quadratic form. So it's a quadratic function. So it's got a constant. Actually, it doesn't have the linear part. Although if your original problem had a linear term in the objective, this would have a linear part too. At the end, you have PT is QT. That's the final cost, and that little one is 0. And then VT, you have a backward recursion from here. This is this thing is VT plus 1 of AZ plus BV plus W. That's what this thing is. Now, when you work this out, it's quite easy to do here because lots of things are zero mean. So, for example, the WT transpose P times all of these two, that goes away because that's zero mean. And the only thing that really comes up here is you have the WT transpose PT plus 1 WT. And that's this. That would you'd recognize this way. Right, because the expected value of WT transpose PT plus 1 WT is that. Right, or people have seen this before, so this is the usual. Let me just write that down just to make sure it's completely clear. It's a completely standard trick. It's sort of like if you want to write the expected value, if Z is, well, actually all I need is this. All I need is this. If I have expected value of Z equals 0 and expected value of ZZ transpose equals capital Z, then the expected value of Z transpose PZ, you write it this way. The first thing you do is you rewrite this thing as the trace of P times ZZ transpose, which looks kind of pedantic and weird here. And you do that, by the way, the way you know that this is right is that trace AB is trace BA. So I could write this as trace PZ times Z transpose is the same as trace of Z transpose times PZ. But then it's trace of a scalar, so it's the same thing. But this thing, the expectation floats inside to the ZZ transpose. You get capital Z, and you get the expected value of PZ, like that. By the way, that's sort of, people write it down that way. That's perfectly good. Everyone understands what this is. But probably there's better ways to write it. So for example, I think this is probably a better way, and which would be one better way. Oop. So that's another way to, that's a pretty symmetric form. So this would be how the sort of a better way. It won't matter, but just for aesthetics. Okay. So this term, WT transpose PT plus 1 WT, the expected value, that turns out to be this thing here. And the rest turns into a familiar Riccati recursion here, because here you just get some quadratic in Z and V. You minimize a quadratic in 2 blocks of variables over 1, and you get a Schur complement. So this is actually a Schur complement. And although you can't really see it that well, you would see it if you pulled out, I don't know, if you pull out, certainly you pull out an A transpose out of either side. Actually, A transpose would be fine here. You pull out an A transpose on either side, and the Schur complement will emerge here for something. Okay, so that's the. So what's nice about this is this gives a completely. This is the one case where you can actually solve a stochastic control problem. It's quite sophisticated, actually. The optimal policy is a linear state feedback. So in other words, it just takes the current state, multiplies it by a state feedback gain, which you get by propagating this Riccati equation, Riccati recursion backwards in time. And the first thing that you notice about the state feedback is that it actually apparently has nothing to do with the statistics of what of what you're up against. I mean the disturbance and also the initial state, which seems kind of weird. So it says basically you take the same recourse no matter what the policy is the same. It doesn't depend on what kind of disturbance you're up against or the covariance of it, which is really a bit odd at first. And the optimal cost is the expected value of V0 of X0, but that's trace sigma 0 plus Q0. But if you go back and look what Q0 is nothing but, you can see that Qt is just a running sum of these things. And so Q0 is simply the sum of these things. And that gives you this formula here. Now this gives there's actually, all of this can be interpreted quite nicely. This is exactly the optimal control that we looked at last lecture. But that was an optimal control problem, not a stochastic control problem. It just said, find me the optimal U to minimize this cost and all that sort of stuff, given what state you're in. And there it was a mere observation that you could write the optimal controller in a linear feedback form. And it was utterly irrelevant in the last lecture. You could give U as a trajectory immediately. You could write it in state feedback form. They were exactly the same. Here, that's not true. This is very important here, because the point is that now you don't know what little xt is until time t. And that's when you make your decision as to what ut is. And it still has this linear form. So these actually have some very nice interpretations. Let me see, we wrote them down. I didn't. Let me tell you what the interpretations of these terms are. This one is quite beautiful. This one says this. It says that I'm going to choose at random an x0 from the distribution of x0. So I'll choose that x0. Then after that, there will be no more disturbances. None. So I'll just start you in a weird initial state, and I'll ask you to maneuver that, well, back to 0, or not quite back to 0, whatever minimizes the cost running forward. If you do that, that is exactly the average cost you run up. That's what this term is. So this term is the cost you would get if the initial condition were generated according to this distribution, but there was no further no further disturbance of the state. Right? In which case, by the way, you could work out what the optimal u is as a function of the initial state. So that's exactly what this term is. This term is actually quite beautiful. It basically says that it's the same thing, but moving forward, it says, for example, at time 3 or something like that, it says imagine that you start from an initial state depending on W3, which is chosen from the distribution W3, but thereafter there's no more disturbance. So that would give you these, and then it basically says that it's the sum of these gives you the optimal cost for this thing, and that's not remotely obvious. I mean, at all. In fact, when you kind of look at it and think that these two are the same, it's just some weird accident having to do with linearity and stuff and quadratic costs and things like that. So it's certainly completely false in general. So that this would be the case. Okay. Well, now I can tell you what how people or one of the methods for solving these problems. One, I mean, maybe it's the simplest one, or it's not the simplest one. I mean, methods for stochastic control are, for one thing, it includes all of control. So all of traditional control, like, proportional plus integral, proportional integral derivative, all that stuff applies. But a simple, sophisticated, the simplest of the sophisticated methods would be certainty equivalent model predictive control. And it works like this. It's just model predictive control, but it's going to work like this. It's time t. You have observed a state trajectory that's utterly irrelevant up here, except in one term only. You've observed a state trajectory 0, x0, x1, up to x little t. And based on that, you form a prediction of what the future disturbances are going to be. If they're independent, that's just like the mean or something, or could be. Right. Oh, by the way, these absolutely do not have to be anything like conditional expectations. So they don't have to be. They can be conditional expectations. By the way, that's no better or worse, because in fact the optimal thing to do is not to use conditional expectations here. But so the point is, they don't have to be conditional expectations. They can be. If you can calculate the conditional expectation, great. These could actually be, these are just forecasts. I mean, they can come from analysts who say, I think the prices are going to look like this, or something like that. It just doesn't make any difference. So this is some prediction of what W tau is going to be. And so what you do is you form this optimal control problem. Now, as of like last lecture, and you're going to run out capital T steps. You're going to run from where you are to the end of the game. You'll run up, but you'll do the accounting for your stage cost and your final cost. You have to satisfy the input constraints. And what you'll do is, for the disturbance, you're simply going to put in these forecasts or approximation. You're just going to plug in the forecast. So it's really like quite stupid. It basically says, do a planning exercise. Do exactly what you would do if your forecast were perfect, right? Which is quite ridiculous. But that's what it is. So the only way in which capital XT comes into this, and in fact this whole thing is actually this is the policy, the arg min of this subject to that. That's a policy, which is to say it's a function of capital XT, and it comes in right through there and nowhere else. So you solve this problem. Okay, so you call this is your plan. And it's a bit silly. These are all, actually not one of these will actually come true. I mean, this is sort of if someone says what's x tilde t plus 1 out to the end, you say, well, that's my plan for what the state trajectory is going to do. You have no reason to believe that's actually what's going to happen. In fact, that's not what's going to happen. That's all quite, in fact, if that's what's going to happen, it means your forecasts are perfect. Then this is the wrong lecture for you. You have to look at the previous one, which is simpler, because then it's not stochastic control. Okay, so you work this out, and then what you're going to do is you're simply going to do this. And then that's your policy. That is the certainty equivalent model predictive control thing. That's your policy. So so it looks dumb. It works actually shockingly well in a lot of cases, and it sort of balances two. It makes two simplifying assumptions which kind of null each other out. One is that it assumes your forecasts are perfect. And the second is that you'll have no recourse in the future. Actually, if your forecasts are perfect, there's no need for recourse. So this combination of two weird, bad assumptions kind of ends up doing something quite good. So, okay. So this is widely used. For example, revenue management. This is a euphemism for extracting as much money as possible from you and me, like the airlines use or something like that. They decide how many seats to release at some price and that kind of thing. So that's revenue management. I like that term. So they're definitely managing the revenue. And I'll give you a hint. It is not in our favor. It's used actually it's also used, I know, in finance for a lot of things. For things like optimal execution and all sorts of other stuff when you have to sell a giant block of asset or pick up a big block, some big block of stock or something like that. So it's used in lots and lots of things. And in fact, it will be used in more and more. Right now it's used in things where things go pretty slowly. I mean, where it's down to a second or even minutes or something like that, like in supply chain optimization. So in real supply chain optimization, that's stochastic control. I mean, unless your forecast says, I'm going to tell you the demand for this product in 3 weeks, and then you say, well, how sure are you? And if the forecaster says, totally, then you're in the last lecture. By the way, the funny part is you do the same thing. That's the same code would run. So it's really just subtleties here. The difference is in that case, it's just a cheap way of just looking ahead and getting out of solving a big problem or something like that, which is actually kind of silly given that the cost of solving problems like this scales linearly with the horizon size. So, okay. So it's used in revenue management. As I said, it's based on two very bad approximations that kind of cancel each other out in a weird way. So you trust your forecast perfectly, and you have no recourse. Actually, if you trust your forecast perfectly, there's no need for any recourse because it means that the future is completely known, and therefore you can decide. There's no advantage to changing how much of some product you order next Tuesday based on a week's worth of new data because your forecast is perfect. So there's no need to. And it works really, really well. By the way, combined with the stuff that we looked at last week, which tells you that these things can actually run very fast, faster by, let's say, a factor of 1,000 or 100 or something like that than almost all people know or suspect, tells you that there's actually plenty of opportunities for this stuff to be fielded in various things, because I mean, not many people. I mean, there are places using this. Oh, one of the problems is when you look around is that no, people don't use this name. The only people who would recognize model predictive control would maybe be people running chemical process plants. And you said, oh, we're using, that's how you solve your stochastic control problem. They would say, what's that? So, and if you look in finance or revenue management, they would say, I'm doing revenue management. Or I'm doing dynamic linear programming is another name for it, or something like that. So you get, okay. So let's look at an example. It's a system with 3 states, 2 inputs. I mean, none of this matters. A horizon of 50. It's a completely random system. We'll have a quadratic stage cost. This is just, the point is this is just made up completely just to see what happens. And the constraint set is, it says that at each set, each input has to be between plus minus 0.5. And then we'll just make all of these inputs in the initial state. It's all they're all just IID with a standard deviation of 0.5. So they're all plus minus 0.5 variables, all of them. So Okay. So here's a sample trajectory. It's a sample trace of x1 and u1. And so this shows you the, the state. And here's the input. And you can see that it is actually saturated, some fraction of the time here. You can see various times where it hits the limit like this. And this is running, this is with the MPC trajectory. Now here, the way you would get this is you generate a random x0 w trajectory. You'd then actually run MPC, which is to say that you'd solve a QP for every one of these points, and you'd propagate it forward and get what you get. Oh, by the way, what's our forecast for the w's? What's w hat of t given tau? Tau given t. What is it? It's 0. Yeah, it's 0 because they're independent and yeah. Oh, by the way, if for some reason you don't want it to be 0, you're perfectly welcome to make it non-zero. So you want to add a hunch in there, you're welcome to. So, but we're using 0. So the way you judge this now is it's unlike last lecture. You can't just run it and say, here's the objective value. You actually have to do this by Monte Carlo. There's no other way. If there are no constraints and then you get a formula. That's the trivial case. In a case like this, just all it takes is input constraints to make this. There's no analytical solution in this case. Now, there are a few problems with analytical solutions, but and so you run Monte Carlo simulations. Now, each Monte Carlo simulation requires you to solve 50 QPs in this case or whatever. So you run, I don't know, a couple hundred or 1,000 Monte Carlo simulations. In fact, that looks like 1,000. Is that the right number? Young? Is this 1,000? Looks like. No, it's really? Because that's 100 right there. I mean, of course, these numbers are totally irrelevant, right? But if you were to add up all these, you'd find out. You might be right. That's 500.
I don't know.
It doesn't matter. 500, 1,000. Anyway, it's some reasonably appropriate number. And the average value is here. And so, of course, this objective is a random variable. It's got some outliers. It's got some things that did very well here because you got a very benign input disturbance here. Oh, by the way, as the horizon gets longer, of course, this gets tighter. But doesn't matter. We're just doing the 50-step version. So this is I'll explain what these two are in just a minute. In fact, I'll explain what all these things are. In fact, let me do that first, and I'll come back. Okay. So here several control laws are going to be checked. We're going to do this. The stupid control law is to calculate the linear quadratic one. So by the way, this is how this would sort of probably work if people implemented it in a dynamical system or something like that. You'd have the state feedback gain, which would tell you U is something or other. If there were no constraints on the input, that linear feedback control law would be exactly optimal, period. Now the problem is when you form KT, XT, occasionally that's outside the bounds of your input, and so you simply saturate that. So that would be this one, and this gives you an average cost of 275. Okay? If you run MPC here, your average is 224. And so you can see it's actually measurably different. And I think you can see that from this picture here. This is this very, very simple thing. And then this is MPC here. So that's a little disturbing, but that's OK. But that's a nature of all this. Actually, if you cared about this, suppose someone said, I don't like all of that compared to that. What's the answer to that? How do you respond if someone says that? There is a correct response, and there's a lot of incorrect responses. What's a correct one? What's the correct one, actually? Well, the correct one goes like this. When this problem started, you agreed to this cost function. The expected value of the cost worked out with this. If for some reason you don't like it when this thing has when that cost has outliers that are big, then you should not have agreed to that cost function. And in fact, you shouldn't have done something like this. You could put a risk-averse term. And how would you put risk aversion into this? We talked about it last time, actually, but it doesn't, I think we did. How would you put risk aversion? No, just suppose you look at this, and someone says, yeah, I've run MPC, and they go, that's terrible. There are lots of times when the cost is high. The stupid saturating controller does better, actually. What would you do about it? How would you change it? Here. I think we talked about it.
Add like standard deviation.
Get out of standard deviation. Do you know how you do that in a convex way?
X transpose covariance X.
No, that won't do it. That won't, because what you want to do is you want to penalize large excursions of LT and little L little t and L big T. You want to penalize large ones, and you're less worried about the smaller ones, right? It'd be like what you do in finance or something like that. What would you do? Oh no, Huber would be much worse. If I replaced those quadratics with Huber, I'm basically saying I'm giving you license to have large residuals, and that would do just the other thing. But you're close, actually. What would do better than that? Well, what's the opposite of Huber? Huber says relax on the outliers, right? Because it just goes linear. That's the most relaxed you can be and still be convex in a penalty function. Barrier. So barrier would do the trick. By the way, if I did a barrier here, what would happen? Can I do a barrier here? It's kind of sort of a subtlety, and it would be a practical issue. You cannot, because the disturbance is Gaussian, and so with small probability, however big you set your barrier, there's a positive probability that the disturbance, through nothing you can do about it, will be outside that barrier, run up a bill of infinity. So you can't do barrier, but you can add like a quartic. But I'll show you the right way to do it, in fact. The correct way to do it is to do risk aversion. And you would simply do this. You don't like, you'd have this thing. It doesn't matter. Let me just do this one. You don't like excursions in X? Then you do this. This is that's your new cost. Okay? So that's your new cost. By the way, it does the right thing. If gamma is really small, then this is basically like that, right? But what this does is it penalizes positive variations more than negative ones. Everybody. So this does the right thing. And when you put the expected value here, that's your new cost function. It does just the right thing. And it's very traditional to do this, like that. So, and this would be the cost. This would be a cost function that is now risk. It would be called a risk-averse, quadratic or exponential of quadratic and whatever. So that's what you would do. By the way, the first term in the expansion is what I can't remember who suggested it, what you wanted. The first term in the expansion here is the variance. So you would get this cost plus the variance. And if you were to do this, it would tighten this up very, very easily. How easily could we do this in, well, I believe, is the source code for this online? Not yet. If the source code were this, how fast could this be? Could we do this? Could we add this? Could we modify this? The source code.
Very fast.
Very fast, right? Because you would just go back in, and wherever you see you grep for minimum, you just find the minimized statement, and you replace it with this thing, and it's done, right? Okay, so the incorrect answer is to complain about these things. That's wrong, And by the way, the same is true, but would actually never happen in finance if you said, I want to do something, and then you work it out and you look at the histogram and there's some outliers, like in this case negative ones, meaning loss or something like that. You don't like those? No problem. Then go back and put in a nice strong concave function that charges you for losses. You don't like losses. And don't complain about it. That's the key. Okay, so this is all on the side. So I guess the point here is that when you started the problem, we agree that it's the average of these that matters, and this beats this quite a bit. This relaxed number, let me show you what that is. The relaxed number is simply this. It basically does the following. It ignores the input constraint. So it's simply it's calculated via the LQR, but via the linear quadratic regulator. So it just propagates backwards, and it actually runs up wherever this formula was. It just calculates this formula. So that's not by Monte Carlo. That's just you run through, add up all these guys, and then that's the exact amount. That's obviously a lower bound, because here the difference between the two is merely that you are more constrained. It simply corresponds to commenting out this constraint. And then you get the global solution. So, because it's one of those special cases. And that says that no one could possibly do better than this here. And what this gap shows you is that, well, it kind of says that you're kind of close. By the way, a more sophisticated relaxation method will make this bound for this instance is, what is it? Like 175 is a more sophisticated bound. You get 175. And actually, at that point, it's quite interesting. I would be happy to argue at that point that for all practical purposes, this is pretty good. Actually, this would be for the quadratic case. And the reason I would say that is this. If that's 175 and that's like 225, you're off by 50 or something like that. But you have to take the square root because these are sort of like squares. So you're maybe something like, at that point, you could argue that you're no more than 15% suboptimal, period. That's it. In this case, for problems like this, when you see objectives that look like this, this would be typical in like dynamic systems with vehicles or traditional control. Usually people don't really mean this. They just mean I want this. This is a code word for please make the state small, not big, right? So because no one really cares about least squares type things. If this was a more intricate function in a finance problem or something like that, or a revenue management problem, then things being like 20% within the global optimum is not, then 5% means something. So when you see an objective function that's likely to actually be the revenue or the loss or the cost or something like that, then you can't be so cavalier about it. But when you see things like this, it's just somebody saying, I'd like the state small. And you can go back and ask questions about that. Like you could say, are you sure you really meant this? Are you sure you didn't mean like 1.1 here or something like that? And if you can ask a couple of key questions and they'll maybe admit it. Okay, so this finishes up this topic. It's quite interesting. I think there's a lot of sort of opportunities for doing this in a whole bunch of different areas. I guess people are already doing it, maybe not in a totally organized way, but in lots of people in lots of fields have already found that, and maybe you'll find it in some others. So. Okay, so any questions about this? Because otherwise we'll go on to we'll just start our last topic. Let's see. How do you do this? Okay, so now we're going to start the last topic for the class, which is on global. It's sort of your intro lecture to global optimization. So that's, by the way, a huge field. You can and do have whole classes on it. I don't think here, but you can have whole classes on this. People do have whole classes. There's like books and books and books written on this. So this is going to be the simplest method, just to show you what these methods look like, the simplest methods of what it looks like to solve a non-convex problem non-heuristically, to be able to say that's the global solution within this or something. So that's branch and bound. So let's go over how that looks. So just to remind you how this works, we've already looked at this earlier when we looked at sequential convex programming. The basic idea is if you have a convex problem, then methods, and it's some standard problem. If you solve it, you always get the global solution. That's not an issue, and it's always fast. Okay, and that's sort of true both in theory and in practice. When you have a non-convex problem, you have to give up one of these. So that's what you have to do. Now, if you give up the always global, you're talking about local methods. We've already looked at one, which is sequential, or a family of local methods based on sequential convex programming. These are local methods. There's lots and lots of those that you can take classes on here, entire classes. In global methods, what you're going to do is we're not going to drop this. So you're going to always get the global solution, and you're going to lose this. They do actually, every now and then, in some application, will actually work quite well. Okay. So we'll look at global optimization methods. They'll find the global solution, and they'll certify it, but they're not always fast. So, and in fact, in many cases, they're slow. So I should say a few things about this. Just to remind you, in convex optimization, there's the idea, well, there's a certificate. What a certificate of optimality or suboptimality or something like that is provided by a dual variable. So you solve the problem. I mean, after a while, you get used to it. I mean, you just solve the problem, and you trust it. You solve an LP, and you get the answer, and you don't check to see if, like, whatever SDPT3 or Sadumi calculated the right solution for you, and it wouldn't have come back with a status of solved or whatever in CVX had it not certified that to some reasonable number of digits it had actually calculated a solution, an exact solution within that tolerance. So the certificates in convex optimization are very simple. They are dual feasible points. So when I give you back a solution, I say, here's the solution, and then the simplest method of certification goes like this. I give you a point which is suboptimal. You verify that it satisfies the constraints. I also give you a dual feasible point. You verify that it satisfies the dual constraints. And you evaluate the objective of the first one and the dual objective of the second. And if they're close, then it means that, in fact, it simultaneously certifies both. So certificates in convex optimization are based on duality. What's going to be really interesting is what does a certificate look like for a general non-convex problem. So, and there's different kinds of certificates, but we'll see what they are. It's a more complicated object. Okay. So branch and bound. It's a family of global optimization methods. You'll find lots of variations on this. There's like branch and cut. They've got all sorts. That's another huge name for this, and they have all sorts of names for this. Actually, how many people have actually taken something on this or seen? No one. Okay. So, okay. So they're going to maintain provable lower and upper bounds on the global objective value, just like in convex optimization. So you will get plots that look very familiar. You could even show something called the gap. It's not the duality gap, which you're used to seeing is duality gap versus iteration. It'll be a gap, and a gap will be the gap between the best point found so far and the best lower bound found so far. That's going to be the gap at any given time. Now these have exponential worst case performance, and in fact they will often be very slow, but actually occasionally, if you're very lucky, they work well. So, okay. I should add that in branch and bound algorithms, you're going to see, like in solving convex optimization problems, there's not much room for personal expression. I mean, not much, right? I mean, you can solve, I can solve it faster than you can or something. I mean, there is, but it's kind of very small. You get to non-convex problems like local methods, huge room for personal expression, right? By the way, that's a way to say these things are totally unreliable and need to be babysat and all that kind of stuff. But if you want to think of it on the positive side, it means that my local method can be way better than yours, which just is weird. And then you would judge it many ways. You judge it by how fast it is. And also, it's entirely possible in a local method that we come up with different solutions. Sometimes yours is better, sometimes mine is better. If mine is often better, then mine is better. And I can always, when I'm doing this, choose the examples where mine is better. So that's what I'm saying. That's nice you get nice personal expression. You're going to get personal expression in a branch and bound method too. We'll see where where the ability for you to put your stamp on this comes in. But the way that will work will be simple. What happens now is we can't disagree. No one can do better than another person. If the rule is to solve the problem globally to certified 1% accuracy, then you can't do that any better than I can do it because we're both doing it and there's no lying and all that. We have to do that. What can change is how long it takes. And indeed, your method of branching and whatever, your bounding method could take 4 seconds and mine might take 2 days to run or something. So that's where that's how you would judge yourselves, is basically just how long it takes to run. Okay. So the basic idea actually is very cool and very simple, and actually the basic idea is quite useful in a lot of cases. In fact, we already signed the last homework, didn't we? I don't know. Do we have recourse? I would say so. I don't know. We'll see. I'll think about it. I just thought it was some good. There was a problem I've been thinking of. I wanted to assign. Oh, well, that's good. I think I even wrote some of it down somewhere. I'm going to find it. Okay, so we'll see. That'll be recourse in action. It'll be simple. Okay, so the basic idea is it relies on two subroutines that hopefully efficiently compute a lower and upper bound on the optimal value over a region. So that's what it is. Now, how do you find an upper bound on a minimization problem over a region? That's easy. You could choose any point in the region and evaluate the objective function. I mean, if it's feasible. Well, if it's not feasible, the upper bound is plus infinity, which is a valid upper bound. It's just not, well, it's not useful, but it's valid. You could run a local optimization method. It really doesn't matter. The lower bound over the region you're going to find by a convex relaxation, duality. You could argue from a Lipschitz or other bound or something like that. And then the way this whole thing's going to go together is this. You're going to partition the feasible set into convex sets, and then you're going to find lower and upper bounds on each in the partition. From the partition, you will then form a lower and upper bound on the global problem. And if they're close enough, you quit. Otherwise, you will partition and repeat. And actually, before we go on, let me just write down the example, and I'll show you what it is. Maybe we won't put it on the homework. How about that? But I'll find this problem because that met with approval. I guess. Okay. So, all right. So let's just solve a problem like this. Let's minimize. Note the period. C transpose x, subject to ax less than b, and then let's do something like this. Let's say that x1 is either 0 or 1. Okay. That's my problem. Okay. How do you solve that? First of all, is it convex? No, not remotely. So I guess the classical method is to when you say it's non-convex, you back off slowly. Do not turn your back. You slowly back away and then make a safe retreat. Right. But actually, how do you solve that? It's extremely easy to solve. How do you solve that problem? Yeah, you plug in 0 and you solve it, and you plug in 1 and solve it, and it's done. Okay. So, okay. How about this one? How about that one? How do you solve that?
Relax it and hope that you get 0
Yeah, that's, I mean methods that don't involve prayer and, or hope or aspirations. So, no, but that would work. That would give you a lower bound. How about, what would you do for this one? Yeah, you could do all combinations if you had to. This is 1,000. You'd run 1,024, right? So you solve 1,000. Oh, and what would the answer be, by the way?
Zeros.
What would it be? No, I mean, how would you get the answer? You'd run 1,024 LPs, and you just take the best one. Okay, so that's what you do. Okay, so branch and bound is going to go something like this. I mean, this is sort of it's basically this idea, but doing it in an organized way where you're going to scale it past 10. You can go to 15 this way and so on. By the way, just for fun, and then maybe we'll get to the main thing next time. Let me ask one more question about this. Suppose you had to solve that problem right there. We had to solve 1,024 LPs, but you had to do it fast. It was taking too long. Your whatever 15-line MATLAB thing was taking too long. How would you? Could you speed that up? Solving 1,024 LPs like this. In fact, let's talk about that. Could you? Oh, you did it in parallel. That's probably the easiest way to speed it up. Is indeed to find 1,023 friends and
Regularization, and then kind of figure out which ones would be 0, and then kind of fix.
Oh yeah, you could get a heuristic. You get real fast by relaxing. I mean, you could also relax and get a bunch of them. By the way, if you relaxed and some of these were slammed up against 0 and some against 1, what can you conclude? When you solve the relaxation, if they were all 0 or 1, what could you conclude?
That's the optimal.
That's the optimal. If they were all 0 or 1, but three of them just were sitting in the middle, what could you conclude? That's the right answer. Nothing. It is very likely that the ones that in the relaxation came out 0 are indeed 0 in the global solution, but it is absolutely not guaranteed. So, okay, so that would be one method. Actually, in something like this, you could do a lot of stuff, and let me just mention a couple. First of all, you can do warm start. Whenever you have to solve a problem with the same structure over and over and over again, with nearly the same, not nearly, I mean, I guess it's not that near when you're taking the first 5 variables and making them 0 or 1. But if that's if there's 1,000 variables there, right, you could use a warm start. So from the previous one. Here would be another trick that would actually be quite useful. Suppose you've solved a bunch of these LPs. Your code is going to have a logic in it that keeps track of the best one you found so far, right? So you're going to maintain something like x best, and it remembers some pattern of these, and then it solved it, and it's the best one. The others, by the way, are out. Anybody worse than x best is out of the running. Okay. When you're actually now solving this problem using an interior point method, you get at each iteration a dual value. That's a lower bound. Everybody see, right? You put logic in there that says the following. If you take a pattern like 0, 0, 1, 1, 0, whatever it is, something or other, you take that pattern and you start solving it, the instant the dual value goes over this, what can you do? You can quit, even though you haven't solved that one of your 1,024 LPs. Why can you quit? Because by convex analysis, you have a proof or certificate that the optimal value of that LP exceeds this. But actually, that means you don't even have to finish solving it. to know that the answer will be worse than the best you've already seen, and therefore you break. Everybody see this? So, and that will work really well because a bunch of these are going to be like way, it's going to be obvious, right? And it won't take the dual value very long to get above the best you've seen so far.
Can the dual value go above C transpose X best, or will it be?
Oh, absolutely. Sure. Yeah, because C transpose X best, that's the best you found so far, right? Now you choose a different initial bit pattern. This was obtained with, 0, 1, 1, 1, 0, I don't know, something like that. And now you're testing this pattern, 1, 0, 1, 1, who knows, right? Like that. What happens is the optimal value of this thing, it may be like over, if the optimal value of this is lower than this, then that's the new winner. That's the new X best. But if it's above it, then the dual value will rise above this value, at which point you break. Now, if it's way above it, which is to say that this is a rather stupid, obviously stupid choice of initial bits here, then the dual value will go up and be 2 iterations and it's all over. So these are just practical matters, but they would allow you to do this a lot faster than it looks like it would have to be if you just did if you didn't do it, if you just wrote a 5-line thing that said for all 1024-bit patterns, evaluate the solve the LP and compare the optimal costs. Okay, so I guess how did that happen? Oh, well, we'll quit here, and we'll continue. This is our last topic next time.